One of the last functions I'd like you to get to use is Legendre quadrature, or Gaussian quadrature as we called it in class. I don't really encourage you strongly to look at this code. It's pretty powerful and has various techniques inside of it which are hard to understand. But to give you a quick rundown, basically what happens is that we use Newton's method, here's all of this, on finding the roots of a polynomial, and those happen to give us the x values of our Gaussian quadrature. That's the first 40-50 lines of code. And then finally at the end, just a couple more short lines, we get the Gaussian weights, and we also remap and scale from -1 to 1 up to a to b, which is something I think that we've worked on in class as well. Okay, and so basically what we can do then is the following. I can run this code, and let's get the x and the w values to be Legendre quadrature. There it is. Okay, and we have to just specify how many points we'd like. So let's do the familiar 3-point Gaussian rule. And if I just put in 3, it'll give me the x values and the w values. Notice that w happens to be 5/9, 8/9, 5/9, and that won't change anything. That's the same values that were just given. Okay, that matches perfectly. And let's look at the x values and note that they are equal to negative square root of 3/5, 0, and square root of 3/5. And if I put a prime there, that organizes them back into a column vector like I had as default output from the code. Why do I have the w's as a row vector and the x's as a column vector? And the answer to that is I like dot products, and let me show you what I mean. Suppose now that I have a function, something like an exponential, let's say, and I want to integrate the exponential function from -1 to +1. Okay, here's how I'll do that. I'll define f, and just for emphasis, let me redefine now. I want the 3-point Gaussian rule, and I'll just hide the output this time. I don't need to see it anymore. And then what I'll do is I'll say that my approx is equal to w times f of x. And that's it. What is the exact value? If we integrate e to the x from 1 to -1, you could find pretty quickly that it's e to the 1 minus e to the -1. And as you can see, those values are pretty close to one another. So we can get the exact and the approximate values and subtract them and form the error. Well, I can do that with increasing levels of accuracy by increasing the number of quadrature points. We could do it with 2, certainly. We could do it with 4, 8. Okay, and yes, it would go on and on this way, but that's not very efficient. Let's try to organize this into a .mlx file with a for loop. So what would we like to do? Well, we would like to have a list of n values. Doubling them is usually a good idea, just in terms of understanding how the error drops away. We would like to take the length of n and set up a for loop going from 1 through that length. And again, what we'll like in here to do is select one of those n values at a time. And then let's see, well, what we're using that n value for is to vary the number of Gaussian points. So x and w will be the Gaussian quadrature rule of n. N is coming from the kth number in the list of n's that I have available. Okay, and so the next thing to do, let's continue on snagging things from the command window then. Approx. The integral won't change inside of my for loop. It's going to be fixed. And it's going to be the integral of some function f of x that needs to be provided below in our for loop. So notice that f and I are related. If I change f, I will change the value of I, but nothing down here really changes. Okay, the last thing to do is perhaps store the error. Let's do the absolute error, the approximation minus the exact value of the integral. Okay, and once we're leaving our for loop, we'll have constructed for each value of n a different value of the integral. So here we can display n, and on a new line, we'll display the error. And if we run all of that, okay, a little messy. Let's start this over. Try that again. Not quite enough room. Well, let me then put it in my view here to do output in line, and it'll go below now. Oh, still not quite doing it. Well, here, let me change the format to short. And we'll run that again. There. Okay. And what do we notice? Well, the errors drop off precipitously fast to the point where it looks like zero error, even with a 4-point Gaussian quadrature rule. Okay. If we display the errors through the command window, we can see, yes, okay, that does appear to be the case. Let me lengthen the format and just display those. And yes, okay, we're the same problem. Perhaps if I prime this, I can at least look at them as a column list. Ah, but notice, yes, very quickly do the errors drop off as we go from a 2-point rule to a 4-point rule, even to the 8-point rule. We have full machine precision on this particular integration problem. Here, let's spice things up a little bit. Let's make this 3 times x, where the exact integral will be e to the 3, plus e to the negative 3, and we'll divide by 3. Okay. And let's see if that factor, that stretching factor of e to the 3x instead of e to the x, gives us any differences with the errors. Now we can at least see at the final decimal there's some error still, but already quite small. Oh, I don't know. Let's say then that a is a tunable parameter. And we'll make it 5 this time, and everywhere I had 3, we'll put a. And that will be the exact value of the integral of e to the ax from -1 to +1 each time. And I can now look as a varies. Ah, there we go. So now I can start to see a little bit more error, but it's still quite small, as you can see. Okay, so 11, huge amount of error with the 2-point rule. It drops to 0.2, and then we've already got 6 or 7 decimals of accuracy to the exact value, which in this case is e to the 5 minus e to the negative 5, etc. Okay, but yes, from here, if you can display n and you can display the errors, you can certainly display then the table that I'm asking for, and you can do this for various functions in the same exact way. If I put primes here, we can also then display this as columns instead of as rows. And maybe that's a little bit more legible.